This is Engineering 245, Lecture 3. Before we get into this week's lecture, let me make a quick announcement regarding the syllabus and how the rest of the class is going to proceed. So in past semesters, when I teach this class, I usually break down Chapter 11 into 2 lectures, right? Because it's a very lengthy topic, the kinematics of particles. And because of this being a 14-week course where each lecture is going to be longer, I was under the impression that I would be able to squeeze all of Chapter 11 into 1 lecture this semester. And therefore, I designed my syllabus accordingly. It turns out, after giving that first lecture, that there was no way I would have been able to squeeze everything into 1 lecture as far as Chapter 11 went. So I ended up having to break it down into 2 lectures again. Okay, so week 1 was kinematics of particles dealing with rectilinear motion. Week 2 was curvilinear motion. Okay, so what that means is everything is now set back as far as the dates on the syllabus are concerned. What we're going to cover today is Chapter 12, when originally I had planned on starting Chapter 13. Okay, so I will make a correction to the syllabus once I get back to the States, but for now, just keep in mind that everything will be pushed back. It still might turn out that I might be able to squeeze Chapter 13 into 1 lecture, because the syllabus says I was supposed to break that down into 2 lectures, but we will see how that goes. Okay, even if I do not break down Chapter 13 into 2 lectures, or even if I do have to, there is an extra day at the end of the semester that you can see I set aside for a review. Okay, so that extra day we actually can use to absorb anything that spills over. All right, so let's just keep that in mind, right? So today is Chapter 12. We're going to move on to the kinetics of particles, which of course is now looking at forces that cause the motion of these particles. Okay, so obviously the main equation that's going to define this chapter is going to be Newton's second law. And we all know Newton's second law as F equals ma. It seems like a very simple equation, but a couple of important things about this equation. The first thing is this is definitely a vector equation, right? It's not a scalar equation, so that means force is a vector quantity. It has components. Acceleration is also a vector quantity. All right? The second important thing about this equation is that even though we just know this as F equals ma, that F, that force, is actually referring to the resultant force, meaning that we can have multiple forces acting on our particle, and F is actually the resultant or the sum of all the forces. All right? So since this is a vector equation, like I said, it breaks down into components. And that's the great thing about Newtonian mechanics, is anything that's a vector quantity, you break down into components, and you could treat each component separately from the others. Okay, they can be treated independently. So you might recall that we dealt with 3 coordinate systems when it came to curvilinear motion. So we're going to apply Newton's second law to those 3 different coordinate systems. All right, so the way that's going to work, okay, is very simple. Okay, in the Cartesian coordinate system, if you recall, this is the coordinate system that you would use if you want information on position as well as velocity and acceleration. Right? When it comes to kinetics, okay, it's very simple. This equation, the second law equation, breaks down into 3 separate equations. You sum up all the forces in the x direction, right? And that has to be set equal to mass times acceleration in the x direction. Then you do the same thing for the y direction and the z directions. Okay, so you get these 3 completely separate equations. As far as the normal tangential coordinate system is concerned, right, we break it down into 2 components. the tangential and the normal directions. In the tangent direction, you sum up all the forces in that direction, and that has to be equal to mass times acceleration in the tangent direction. Now, in a normal tangential problem, you would usually not have acceleration in the tangential direction, right? And out in the real world, you usually wouldn't have it directly. What you would usually need is velocity as some function of time, okay? And once you have that velocity as a function of time, okay, whether through experiments or whether, in our case, someone just gives it to you, you just differentiate it to get dv dt, which is acceleration. Okay, so that's the tangential direction. Then in the normal direction, you take mass times acceleration in the normal direction, and you recall that acceleration in the normal direction is velocity squared divided by the radius of curvature. So that's v squared over rho. And finally, in the radial transverse coordinate system, okay, my slides kind of skip around here, but it's in this slide. You have two components again. Right? You sum up all the forces in the radial direction, like on the bottom here, and that should be equal to mass times acceleration in the radial direction, where acceleration in the radial direction, if you recall, is equal to r double dot minus r theta dot squared. Okay? And then in the transverse direction, it's mass times acceleration in the theta direction, or the transverse direction, which of course was r theta double dot plus 2 times r dot theta dot. Very important that you remember from last time that in order to use the radial transverse coordinate system, you need two functions. Right? You need a function that describes how theta changes with respect to time and how r, or your radial dimension, changes with respect to time. Okay? If you don't quite remember this, go back and review the material from that second lecture. Okay, so these are our equations of motion, and we can go ahead, right, and now apply these to a variety of different problems dealing with Newton's second law and forces acting on objects. Okay, so let's go ahead and work out a couple of examples. Let me go back here, right, and we will start going through some examples.